In this video, we'll talk about how we can use complex numbers to help us analyze power series. So the idea I want to think about here is let's start by taking just a power series and we want to think about plugging in complex numbers here instead of just real numbers. Why does this work? Well, how did we analyze convergence for these series? We did this via the ratio test. And the ratio test looks at a limit of absolute values. Now, we have an idea about absolute values for complex numbers. It's called their modulus. And so you can think of this not just as absolute values, but as the modulus of a complex number, and all the same arguments still work. If this ratio is less than 1, then it converges, bigger than 1 it diverges, check on the endpoints as before. But what does this mean if we're looking at this as complex numbers and not just real numbers? Let's take one of the examples we had before. We'll look at the series for 1 over 1 minus x. We had this before. Great. This we knew was the sum n from 0 to infinity of x to the n, and we knew this converged for x less than 1, at least by the ratio test, and then you check the endpoint and see it also converges at minus 1. But now let's think instead if I want to plug in all complex numbers instead of just real numbers. Well, the ratio test still tells me I converge for the modulus of x less than 1, but if we look at the picture of this now, the issue we have is at 1. It's at this point here where my series blows up, because then it becomes divergent, and that's where this also doesn't work. But if I look at all complex numbers with this condition, what does that give me? That's a circle in the complex plane, or a disk. This entire area here, it's a disk of radius 1. Hence the term radius of convergence from before. It is the radius of this disk in the complex plane where this series converges. So think about what real numbers this converges for, which in our case was exactly this interval of real numbers where it converged. We can think about the set of all complex numbers where it converges. That gives me a disk in the complex plane, and the radius of that disk is the same as the radius of convergence that we get from our normal methods for looking at power series. And now we see one other way where complex numbers come into play here. And that's the idea of another expansion that we had before, 1 over 1 plus x squared. We found when doing our work in power series sections that this had a radius of convergence of 1, which we got because it looks like 1 over 1 minus negative x squared. We plug in our x squared into the x from before, we get that this has a power series expansion with that radius of convergence. But this function is defined and nice and smooth for all real values x. Right? So the radius of convergence should be everything because the function works everywhere. So why wouldn't the series do the same thing? Well, the issue here is complex numbers. It's defined for all real numbers x, but there are complex numbers where it's not defined. And that's where the problem comes in. Namely, this function, if I look at this f of x up here, f is not defined at plus or minus I, because at those points the denominator is 0. So if I look at my complex plane again, I now have problematic points at plus I and minus I, where this is the real axis, this is the imaginary axis, which means my disk, where this thing converges centered at 0, can't go beyond those points. So the biggest it could be is the same disk of radius 1, because it blows up at plus or minus I. Right? This disk can't expand past that point because we know the series can't converge to the function at plus or minus I because the function is not defined there. So my disk can't go beyond that point, so it's trapped and can only have a radius of 1, even though the function is nice and defined for all real numbers. So what's our conclusion here? If there's a place where this function does not exist in the complex plane, that finds a point where this series cannot converge, because it can't converge to a function that doesn't exist at that point. That tells me a point that must be at least on the boundary of the system, not outside the disk, in which case I then have an upper bound for what the radius can be, because the radius cannot reach that point and go beyond where that point is. So I can look for points in the complex plane where my function is not defined. This includes real values as well because they're also part of the complex plane. And those give me points where my series cannot converge. And so if I have a center point, I can sort of expand out from that center point until I hit one of these issue points, and that will give me the point at which my radius of convergence has to be, because it can't go beyond that point, and it's going to converge everywhere inside that. And this gives us a way to think about the radius of convergence, as well as how this has to work if we view it as a complex setup as well, and not just a real numbered setup. So I show that the function f of x is x over x to the fourth plus 64 is undefined if the four complex numbers given by plus or minus 2 plus or minus I. Use this fact to show that the radius of convergence is no more than 2 root 2. And then find the actual power series. So basically, I want to take each of these complex numbers and raise them to the fourth power and see what I get. Well, if I look at 2 plus 2i and I square it, I get 4 plus 8i plus 4i squared. But 4 plus 4i squared is 0, so I just get 8i. And therefore, if I were to square that, I would get minus 64, which is good. If I put a minus sign in here, I get a minus sign in here, I get a minus 8i. Square that, I still get minus 64. And the same thing go for the other numbers as well. If I look at minus 2 plus 2i squared, that gets me a 4 minus 8i plus 4i squared, which is again negative 8i. And if I put a minus in here, I will get a plus here and a plus here. Again, all those squared is minus 64, which means they all are roots of x to the fourth minus 64. So what does that mean? Well, that means if I try to build a power series centered at 0, I know I have these 4 points at 2 plus 2i, at minus 2 plus 2i, at minus 2 minus 2i, and at 2 minus 2i, where my function is not defined, and so where the series cannot converge to that point. So that means that the max radius of convergence is the length to all of these points, which is 2 root 2. Because each of these points is at 2, 2 in one of the quadrants, the radius here is square root of 4 plus 4, which is 2 root 2. And I can then build my disk around those points. Now, let's find the actual power series and see if this is the actual radius. So I'm looking for the function x over x to the fourth plus 64. I know I can write this as an x over 64 times 1 over 1 plus x to the fourth over 64. That looks like a 1 over 1 minus x sort of situation, so I can write this in power series. Sum from 0 to infinity of negative x to the fourth over 64 the n, or a 1 over 64, sum from 0 to infinity, negative 1 to the n over 64 to the n times x to the 4n plus 1. And then if I look at ratio test here, to find this convergence, I will get that I need rho, which is the limit n goes to infinity, 1 over 64 to the n plus 1, x to the 4n plus 5, over 1 over 64 to the n, x to the 4n plus 1 is my rho. It's going to be less than 1, which is going to happen when x to the fourth in absolute value is less than 64, which is absolute value of x less than 2 square roots of 2. So I get the same radius this way that I got from the other method. And that's the other way that complex numbers really show up in this stuff from Calc 2, and that's an idea of power series. And this fact that its radius of convergence really is a radius of a disk, not just the width of an interval. And so if you think about it in this disk format, we can then see, okay, where could this radius be, given that I can find where these functions are not defined, because they're not defined at complex numbers of a certain modulus, as opposed to just the real numbers where they might be everywhere, might define everywhere, might be great. But when they break at complex numbers, that causes this radius of convergence also to be smaller, and then lets us define these radii in different ways and figure out what they are for the different power series that may have seemed sort of strange before, can make more sense when rooted in this complex numbers format for what these radii of convergence are.